Good afternoon, everyone. My name is Ernie, and today I will be presenting a research paper titled Breaking Position Invariant Object Recognition by David D. Cox et al., which was published in Nature in 2005. Objects can be recognized regardless of their position on the retina, but we don't know how much about this work. The main question in this paper is what are the mechanisms behind this ability and how neural processes involved in achieving this? Let's talk about the methods. Researchers conducted three experiments with human participants to investigate position invariant object recognition. They took advantage of the fact that we are temporarily blind during eye movements. Experiments included two phases, the exposure phase and the test phase. During the exposure phase of the experiment, the participants were randomly exposed to two different types of trials, normal exposure and swab exposure. These trials were randomly interleaved, and each participant received an equal number of presentation of all objects in each retinal location. In normal exposure trials, as we can see in the figure, the object identity remained the same throughout the trial, and the same object was presented to both the peripheral retina pre-saccade and the central retina post-saccade. This served as the baseline condition. In the swabbed exposure trials, without informing the participants, one object was swabbed for different object during the eye movement. As a result, one object was presented to the peripheral retina before the saccade, and a different object was presented to the central retina after the saccade. This introduced altered spatiotemporal statistics during the exposure phase. More examples for the object presented to the participants are shown in figure B and C. Participants in experiment 1 were exposed to altered spatiotemporal statistics across retinal position for 2 days. On the other side, experiment 2 had a shorter exposure phase, which conducted over 1 day. In the replay exposure phase, which is experiment 3, a group of 12 subjects participated. Each subject was paired with one of the 12 subjects from experiment 1. The goal of this phase was to recreate the same visual exposure that the counterparts in experiment 1 had experienced. During this phase, the subjects were instructed to fixate their gaze on a central point on the screen. Objects appear first in their peripheral vision and then moved to the center of their gaze, following the exact timing of eye movements made by their counterparts in experiment 1. The screen remained blank during the time when the eyes of experiment 1 subjects were in the motion, simulating the lack of clear vision during rapid eye movement. The subjects in experiment 3 were unaware that different objects were being presented during the swab trials. They were asked to perform a task where they had to determine if the object appearing in the periphery and the object appearing in the center of gaze were the same or different, even though different objects were actually shown during the swab trials. The replay exposure phase aimed to replicate the retinal exposure of experiment 1 subjects, allowing researchers to study the effect of altered visual experience on object recognition. Let's dive into the results. After the exposure phase, participants in experiment 1 demonstrated a significant effect. They were more likely to confuse object pairs across retinal position where the objects had been swabbed during exposure compared to positions where the same object hadn't been swabbed. As shown in the result figure, the effect observed in experiment 1 was statistically significant with a p-value of 0.00282. Results of experiment 2 are similar to experiment 1. The participant also got confused. The effect observed in experiment 2 was statistically significant, with a p-value of 0.022. Interestingly, participants in experiment 3 didn't experience the same confusion as the participants in the first experiment. In conclusion, this research demonstrated that exposure to altered spatiotemporal statistics across decades leads to confusion in object recognition, supporting the notion that position invariance can be disturbed by brief exposure to altered visual experiences. Understanding these mechanisms can help us develop better artificial vision systems and further our knowledge of human perception. Thank you for your attention.